particular kind of equation that we can often come across is the quadratic equation. This is an equation where the variable has a squared term. The general form is this: ax squared plus bx plus c is equal to 0 for some a not equal to 0. It can be positive or negative. Quadratic equations are easy to solve. We simply apply this formula, the quadratic formula, to our solution. X is equal to minus b plus or minus the square root of b squared minus 4ac, and all that divided by 2a, where the a's, b's and c's are the coefficients from the quadratic equation, a, b and c. We have some conditions for this formula to work. First, we need a quadratic equation, so a is not equal to 0, and then the term in the square root sign has to be greater than or equal to 0. So this term here naturally can't be negative. Let's look at why that condition holds. Well, apart from the fact we can't take the square root of a negative number. First, let's look at a quadratic function instead of a quadratic equation. So instead of letting ax squared plus bx plus c equals 0 and solving for particular points, we're just saying, let's look at how that function changes. So instead of letting ax squared plus bx plus c equal to 0, we just see how that function changes as we change x. We'll look at the case where a is positive, and we'll see next week that gives our quadratic function a particular shape. And we'll look at the case where b squared minus 4ac is greater than 0. So our quadratic function then looks something like this. Our solutions, x1 and x2, are where our quadratic function fx cuts the x-axis. So if b squared minus 4ac is greater than 0, then our function actually cuts the x-axis and we have solutions. Let's look at the case now where we have b squared minus 4ac is less than 0. So a negative square root there. Again, if we have the case where a is positive, but this time b squared minus 4ac is less than 0, what we have is a quadratic function that doesn't cut the x-axis. So we don't have solutions. There's no points where our function is equal to 0. Our solutions for x from the quadratic equation are x1 and x2. So once we have those, we can factorise our quadratic equation. We have ax squared plus bx plus c is equal to a times x minus x1 times x minus x2. Let's remember these minus signs. Sometimes we can factorise a quadratic equation by sight. This is the case where a equals 1. So if we have a quadratic equation of this form, x squared plus px plus q equals 0, sometimes we can look at that and see that two numbers, x1 plus x2, add up to minus p, so the coefficient for x there, and when we multiply them together, so x1 times x2, that product is equal to q. For example, if we have x squared plus 2x minus 3 equals 0, what numbers add together to give minus p? So minus p in this case would be minus p is equal to minus 2, and q is equal to minus 3. What numbers multiplied together give us minus 3 and then add together to give minus 2? Well, the solution there is x1 is equal to minus 3, x2 is equal to 1. Remembering that we subtract x1 and x2 from x when we factorise, that will give us that x squared plus 2x minus 3 equals 0 is the same as x plus 3 times x minus 1 is equal to 0. can also solve quadratic equations by completing the square. We'll look at how we do this in an example. So here's our example. 2x squared minus 2x minus 40 is equal to 0. We'll solve that using the quadratic formula, and we'll factorise, and then we'll solve it by completing the square. You can stop this video now and have a look at those examples, or look at them later. Here's an economic example of a quadratic equation. We have a demand function and a supply function, and we know that at equilibrium, quantity demanded equals quantity supplied. What we can do then is solve for P, the equilibrium price. We can see this point here. That's our equilibrium quantity and equilibrium price. Notice though that we have quantity on the horizontal axis and price on the vertical axis, even though price is the independent variable and quantity is the dependent variable. We'll discuss this more when we talk about functions in lecture 3. At equilibrium, quantity demanded equals quantity supplied, so we can equate those two equations. We'll have on the left-hand side 4 minus p squared, on the right-hand side 4p minus 1. We can rearrange that and we get a quadratic. P squared plus 4p minus 5 equals 0. So solving that gives us possible solutions to our equilibrium price. We could solve this quadratic equation using our quadratic formula. Let's do it by plotting the quadratic function. So we have our function there, we plot it, and we see where it cuts the p-axis. So it cuts it at two places, p equals minus 5 and p equals 1. However, we know from economics that our price is going to be greater than or equal to 0. We don't often have negative prices. So minus 5 is not a solution. Our solution is that p equals 1. And then we can go on and find our equilibrium quantity as well. Let's finish this module with a quick look at solving other nonlinear equations. I just want to illustrate 2 points here with 2 examples. Sometimes we can find partial solutions of more complex equations. For example, here we have in example 12, x times y plus 3 times z squared plus 1 times the square root of w minus 3 is equal to 0. We can't solve this completely, but we can find some solutions. Well, we know that one solution will be that x is equal to 0. That will make the left-hand side equal to 0. Next, we could have y is equal to minus 3. Again, that will make the left-hand side equal to 0. We could also have w is equal to plus 3. So we have 3 possible solutions there. We can't say what z will be. Given this equation, it could take any value because this factor is always positive. If we had some more equations, we could find some other solutions. So there's an example of finding some partial solutions with the equation we have. In example 13, I just want to highlight that we need to be careful in cancelling a factor when it may actually be equal to 0. So we have x squared minus 3x cubed is equal to 0. We can factorise that. So x squared 1 minus 3x is equal to 0. There might be a temptation to divide both sides by x squared and be left with 1 minus 3x equals 0. But we have to remember that one solution there is x equals 0, and the other solution is that x equals 1/3. That completes our look at quadratic and nonlinear equations. Our next module deals with solving simultaneous equations.